Assalamualaikum and good afternoon. This is Operating System News. Critical Section Problem. Consider system of n processes and each process has critical section segment of code. Process may be changing common variables, updating tables, writing files and extra. When one process in critical section, no other may be in its critical section. Critical section problem is to design protocol to solve this. In each process must ask permission to enter critical section in entry section, may follow critical section with exit section, then remainder section. Solution to critical section problem has 3. First, mutual exclusion. If process P1 is executing in its critical section, then no other processes can be executing in their critical section. 2. Progress. If no process is executing in its critical section, and there exist some processes that wish to enter their critical section, then the selection of the processes that will enter the critical section next cannot be postponed indefinitely. Third, bounded waiting. A bound must exist on the number of times that other processes are allowed to enter the critical section after a process has made a request to enter its critical section and before that request is granted. Assume that each process executes at a non-zero speed. No assumption concerning relative speed of the end processes.
Next is synchronization hardware. Many systems provide hardware support for implementing the critical section code, uniprocessors, which is could disable interrupts. It is currently running code will execute without preemption. It is generally too inefficient on multiprocessor system. We will look at 3 forms of hardware support, which is memory barriers, hardware instructions, and atomic variables. Memory barriers. Memory model are the memory guarantees a computer architecture makes to application programs. Memory models may be either strongly ordered, which is where a memory modification of one processor is immediately visible to all other processors. Weakly ordered, which is where a memory modification of one processor may not be immediately visible to all other processors. A memory barrier is an instruction that forces any change in memory to be propagated, made visible to all other processors. Hardware instructions. Special hardware instructions that allow us to either test and modify the content of a word or to swap the contents of 2 words atomically, uninterruptibly, which is test and set instructions, and compare and swap instruction. Mutex locks. Previous solutions are complicated and generally inaccessible to application programmers. OS designers build software tool to solve critical section problem. Simplest is a mutex locks. Protect a critical section by first acquire a lock, then release the lock. Boolean variable indicating if lock is available or not. Calls to acquire and release must be atomic. Usually implemented via hardware, atomic instructions such as compare and swap. But this solution requires busy waiting. This lock therefore called a spin lock.
Semaphore. Synchronization tools that provide more sophisticated ways than mutex locks for processes to synchronize their activities. Semaphore S is integer variables. Can only be accessed via 2 invisible atomic operation, which is wait and signal, definition of the wait operation, and definition of the signal operation. Semaphore usage. Counting semaphore, integer value can range over an unrestricted domain. Binary semaphore is integer value can range only between 0 and 1, same as a mutex lock. It is solve various synchronization problems. Consider P1 and P2 that require S1 to happen before S2. Semaphore implementation must guarantee that no 2 processes can execute the wait and signal and the same semaphore at the same time. Thus, the implementation becomes the critical section problem where the wait and signal code are placed in the critical section. It could now have busy waiting in critical section implementation. But implementation code is short, little busy waiting if critical section really occupied. Note that application may spend lots of time in critical section and therefore this is not a good solution. Semaphore implementation with no busy waiting. With each semaphore, there is an associated waiting queue. Each entry in a waiting queue has two data items: value of type integer and pointer to next record in the list. It has two operations. First, block. Place the process invoking the operation of the appropriate waiting queue. The second is wake up. Remove one of the processes in the waiting queue and place it in the ready queue.
Monitors, a high-level abstraction that provides a convenient and effective mechanism for process synchronization. Abstract data type internal variables only accessible by code within the procedure. Only one process may be active within the monitor at a time. Condition variables. Condition X, Y. Two operations are allowed on a condition variable. X wait is a process that invokes the operation is suspended until X signal. X signals resumes one of processes that invoke X wait. If no X wait on the variable, then it has no effect on the variable. Condition variables choices. If process P invokes X signal and process Q is suspended in X wait, what should happen next? Both Q and P cannot execute in parallel. If Q is resumed, then P must wait. Options include signal and wait. P waits until Q either leaves the monitor or it waits for another condition. Signal and continue. Q waits until P either leaves the monitor or it waits for another condition. Both have pros and cons. Language implementer can decide. Monitors implemented in concurrent Pascal compromise. P executing signal immediately leave the monitor. Q is resumed. Implemented in other languages including Mesa, C, and Java. Resuming processes within a monitor. If several processes queued on the condition variable X and X signal is executed, which process should be resumed? FCFS frequently not adequate conditional wait construct of the form X wait, where C is a priority number and process with the lowest number, highest priority is scheduled next. And now, meet Zainatul Izwani at the OS Convention Center will highlight several current issues in operating system.
Thank you to Alia and Ain in the studio. Let's get to the current issue, which is Core i5 versus Core i7 and what would be better. Intel Cores i5 and i7 CPU are still the most popular processor you can buy. But what is the difference between them? Like most computer components, there are dozens of models of each tier to choose from, and it can get a little overwhelming. For most people, a Core i5 like the 8400 is going to be the most sensible choice, especially since the latest generation i5s are typically comparable to the previous ones, i7s. While there are a lot of factors in determining overall system performance, a Core i5 processors won't usually end up bottlenecking your day-to-day performance. Most people, including gamers, will find a Core i5 is perfectly adequate. A Core i7 CPU like the 9700K makes sense only for users who don't mind paying a premium for more power, or for users who often run demanding software like AAA video games at high frame rates, perform video editing or render 3D objects. It is the best performance is what you are looking for. It is Core i7, that is unless you want to bump up to Core i9. Core i5 versus Core i7 on the desktop. Desktop Core i5 and i7 CPU can be most typically separated by the number of supported threads and clock speeds, while both tend to have the same number of processor cores, 6 for the 8 and 9 generation and 4 for older ones. Some have support for additional threads thanks to Intel's hyper-threading technology. That means that they can support twice the number of threads, making them better at multitasking. Typically, all Core i7 CPUs support hyper-threading on desktop, while the Core i5s do not. That was still true with the 8th generation chips like the Core i5 8600K and Core i7 8700K. With the 9th generation though, hyper-threading was reserved for the Core i9 parts only. So the i7 9700K only support 8 threads. Core i5 CPUs like the i5 8400 typically have lower clock speeds too, though not significantly so. They also tend to have smaller cache size. meaning they don't perform as well at repetitive tasks. The added thread counts, clocks and cache does mean that Core i7 CPUs like the super powerful 8700K offer better performance, but it comes at a cost. As our guide to the best Intel CPUs points out, higher-end i7 chips can be a lot more expensive. That 8700 retails at $370, while the gamer's favorite Core i5 8400 can be had for $220. Core i5 versus Core i7 on laptops. Mobile processors are a slightly different story, where desktop Core i5s never feature hyper-threading. Some mobile versions do, allowing mobile dual-core i5 processors to handle extra threads at once. Core i7 CPUs are still more powerful though, where the 8th generation Core i5 CPUs have 4 cores and support 8 threads. Most Core i7 chips have 6 cores and 12 threads. You can usually tell a mobile chip by its naming convention too. A high-end gaming laptop might sport a Core i7 8750H. Like the desktop 8700K, it sports 6 cores and 12 threads, but its clock speed is noticeably lower, especially when it isn't boosted to help maintain lower temperatures. Older generations have lower core and thread counts, with some dual cores in the mix, like the Skylake powered Core i5 6300U, which is a dual-core chip with support for 4 threads. The performance differences between Core i5 and i7 CPUs are roughly comparable throughout generations though. Overall, Core i5 and Core i7 chips differ in the way they handle processing information. Core i5 processors typically have fewer cores and can therefore support fewer simultaneous threads. These threads are used by software to manage multiple tasks simultaneously, rather than queuing everything up for execution one by one. In other words, they are not as good at multitasking. Still, they are great for most PC users, which is why we recommend the Core i5 8400 as the best Intel CPU.